Hello class, Professor Anderson here. Let's talk about the gravity that you experience at the center of the Earth. Okay, let's pretend somehow you dug a hole and you got yourself to the center of the Earth and you stood there and you wanted to measure the gravitational force that is acting on you. What do you guys think? What do you think the gravity is at the center of the Earth? Let's say you did this experiment, you dug out a hole, you stood in the middle of that thing, and you said, all right, what do I feel? What do you think? Yeah, Ryan, what do you think? What's the gravity at the center of the Earth?
I don't know an exact number, but it's going to be a lot stronger than the 9.8.
Okay, a lot stronger than 9.8. Why do you think it's going to be a lot stronger than 9.8?
Because your radius isn't going to be like on the crust, it's going to be 0 since you're right in the middle.
Okay, since we know that gravity goes like 1 over r squared, if I go down to r equals 0, it seems like it should go up a lot, right? And in fact, shouldn't it go to like infinity if we're at the center of the Earth? Okay, that's not quite right, because why?
Well, I think like based on the equation you showed us earlier, like r squared was on the bottom, so if that technically is 0, you're going to divide everything by 0.
Right.
So force should be 0.
Well, no, if it's dividing by 0, then it's going high, right? It's going to
that's
infinity, right? And that is, in fact, what happens if I take all that matter and condense it into a very small point. If I took the entire Earth and condensed it into one point, right? I would need something bigger than the Earth to make this, of course, but let's say I had something that was 10 times the mass of the sun, and I compressed it all into one point. Those do exist in the universe. What are those things called?
Black holes.
Black holes, right?
Professor Anderson here is taking the hypothetical of pressure to condense a very large mass 10 times the mass of our sun into one point, or perhaps a volume in space the size of the Earth. The professor said this might create a black hole. However, I think this is a misunderstanding. My theory of the black hole begins as a center of gravity of a huge mass that is a galaxy made of many objects, and a galaxy is actually organized by gravity into one object, with the center of gravity often theorized to be a black hole. The professor wants to keep the total volume of Earth constant, compress the matter of Earth down, build it back up with compressed matter until he builds a black hole out of it, with the same volume in space as the Earth. Yes, students, this is the start of Professor Anderson's proof of his theory of gravity, by way of an experiment so remote that it seems like fantasy. But, let us go on. But first, here is a video clip of the theory I believe in, that gravity organizes all objects, by way of their centers of gravity individually plus combining them. Here we see one galaxy made up of many objects, moving in an organized manner, and we zoom the camera in on the black hole's center of gravity located at the center of the galaxy, with the black hole circling the center of gravity of the entire galaxy. This is very different from Professor Anderson's theory of gravity. The motion of the galaxy as a whole is organized and rotates like a pinwheel. Star formation happens at a center of gravity, producing pressure for nuclear fusion, and finally, the center of gravity of the entire galaxy creates a black hole rotating synchronously with the rest of the galaxy.
That's a black hole. And the force of gravity increases a whole lot when you get near a black hole. But this is a little different, right? Because I, in fact, carved out a little space in there. So I'm not really up against the mass of the Earth. I'm standing in the center of this hole. Any other thoughts on what the gravitational force is if I do that? Any other guesses out there? Come on, let's come up with some wild guesses. Let's go back to this picture for a second. If I'm standing here at the surface of the Earth, what is the force of gravity on me? Thomas, what's the force of gravity on me up there?
Negative g.
Okay. Negative, we draw with an arrow down. It's got a value of g. I have to multiply by my mass, of course. And so it's mg. What about when I'm over here? Austin, what do you think? What's the force there?
mg, then upwards towards the center.
mg upwards. And look, if I'm over here, then it's mg that way. And if I'm over there, then it's mg that way. So Austin, what do you think? What's the force at the center of the Earth?
I would think it would encompass you and cancel each other out.
Exactly right. The force at the center of the Earth is equal to 0. There is no gravity there. Specifically, there's no gravitational force. Why is that? Because every chunk of the Earth is pulling on you. But I have a chunk of the Earth that's pulling me that way, and I have a chunk of the Earth that's pulling me that way, and I have a chunk that's pulling me that way, and I have a chunk that's pulling me that way. And they all cancel out. And so if you are in this little cavity at the center of the Earth, there is in fact no gravity at all.
And now, ladies and gentlemen, we see the great flaw in the professor's theory of gravity. Gauss's law for gravity only applies to the surface of the Earth and on upward. It does not apply below the surface of the Earth. Only the flux of gravity above the surface of the Earth is subject to the inverse law of radius, and this inverse law applied to the gravity flux at the surface gives a value for acceleration of gravity at 9.8 meters per second and diminishes as one goes upward away from the center of gravity to the surface. The radius value comes from the center of the Earth, where the positive charge of the mass of protons has organized into a focal center, up to the surface of the Earth. It is no coincidence that this is the radius value used in Gauss's formula. Below the surface of the Earth, all of the matter of the Earth has become organized into a focal center at the center of the Earth, and that center is where gravity is strongest. The strength of the pull of gravity then diminishes from that center until it is 9.8 meters per second at the surface of the Earth. However, Gauss never intended for his inverse law for radius be used for the strength of gravity below the surface of Earth. Both the strength of gravity and the heat produced increase as you go downward from the surface to the center of the Earth.
It's kind of cool, right? We should do that. That'd be a great laboratory. I heard it's a little hot down there, though, so might be hard to get there. Okay, let's ask a follow-up question now. We know that the force due to gravity as a function of radius eventually is going to do this. If this is the radius of the Earth, it's going to fall off like 1 over r squared, right? If I start at the surface of the Earth and I go up, it's going to fall off like 1 over r squared. But what about in between the center of the Earth and the surface of the Earth? We know the surface of the Earth has a force equal to that. We know the center of the Earth has a force equal to 0. How does it get from there to there? It turns out, this is a complicated proof, but not impossible. It turns out it is linear. It increases linearly as you go up this tunnel towards the surface of the Earth. It reaches a maximum when you are at the surface of the Earth, and then it falls off again like 1 over r squared as you go away from the surface of the Earth. And you can prove this using something called Gauss's law. So if you keep going in physics, look out for something called Gauss's law. it's kind of a nice little proof. All right, questions? Any abstract questions about doing experiments like this? Yeah, Thomas.
Since gravity is decreasing as you get to the center of the Earth, could you theoretically, like, if you had a humongous hole and heat wasn't an issue, could you jump through the center of the Earth, or jump through one side of the Earth, and would you stop in the middle, or would you just keep going to the other side, like to China?
Excellent question. Let's take a look at that picture and see if we can make some sense of it.